Today we will be talking about the Bradley-Terry model, a model for paired comparisons. The Bradley-Terry model estimates the relative skill level of entities based on the outcomes of paired comparisons. The probability of I greater than j equals the probability of I divided by the probability of I plus the probability of j. Probability of I is a positive score assigned to entity I greater than j can be interpreted as I beats j, or I is preferred to j. This model is widely used in sports analytics, chess ratings, and machine learning. The model can predict outcomes, but it is more commonly used in reverse to infer scores, probability of I, given a set of observed outcomes. Okay, so why this formula? This formula has several intuitive properties that make it a suitable choice for modeling pairwise comparisons. Normalization. The denominator, pi plus pj, ensures that the probabilities of the two possible outcomes, either I beats j or j beats I, sums to 1. Okay, now, so before we get too far ahead of ourselves, let's look at what some made-up data would look like. So here we have a win matrix of Alice, Bob, Charlie, and Diana. And in the bottom left corner, we have the total likelihood equation. The two bars are basically kind of like a summation, but it's multiplication. And then where I does not equal j, that just means like they can't play against themselves. So we have, Alice, that's why there's this tick mark here. So Alice cannot play against themselves. So we go Alice versus Bob, and then Alice beats Bob 6 times. Alice plays against Charlie, beats Charlie 4 times. And then here we have the total wins here. So now for a single comparison where I beats J, the probability is that, which we've discussed this already. If the outcome occurs W to ij times, the pair probability becomes to the power. So let's take a look at what the total likelihood equation looks like when it's expanded out for our specific data. So the probability that Alice beats Bob 6 times is this probability. Probability that Alice beats Charlie 4 times is this. And so on, just for repetition, pick a probability of Charlie beating Alice 1 time is here. So we have, Charlie beats Alice 1 time. And down here we have the probability of Diana beating Alice 0 times. That is also represented in here. Which, that just, anything to the 0 power just simplifies to 1. So I could have just omitted these 0 powers, but just for completion's sake, I'm showing them now. So now let's assume all of the players have the same strength. They are all equally strong at 1. And so we replace all of their strengths with 1. And then that will simplify to 0.5. And as you can see, 0.5 to the 29th power is a very small number. So it's very unlikely that they are all equally strong. Another way to think of it, imagine flipping a coin, and the probability of getting heads is 0.5. The probability of getting heads 5 times in a row is 0.5 to the 5 power, which is like 0.03125. About 3% chance of that happening. So now, in this particular example, imagine flipping a coin and getting heads 29 times in a row. Very, very unlikely. So also, calculating it like this, we also have another problem that's known as numerical underflow. This happens when a computer tries to store a number that is smaller, closer to 0, than it can handle, causing it to be rounded to 0, which erases all the information. This little table that I did as an example, we were fine with, but the larger data sets, It doesn't take very long for us to just lose all of the information due to rounding error. That's where the log likelihood function comes into play. All right, so let's take a look at that now. Okay, and to convert from multiplication to addition, we can use the properties of logarithms. So we'll want to take the natural log of both sides. And here we have it expanded. As you can see, the multiplication turns into addition. Now let's go back to our example where we assume everyone is of equal strength. We have, 29 ln of 0.5 is roughly negative 20.097, which is a lot nicer of a number to work with for statistical analysis. So now this poses the question, how do we figure out each player's strength given our data? How do we start working backwards? And so, in my opinion, the most elegant thing about the Bradley-Terry model is their update algorithm, pi to the power k plus I. This is the new improved strength estimate for player I that we are calculating. The k plus 1 just means at step k plus 1. Pi to the power k and pj to the power k. These are the current strength estimates from our previous step k. Wi, this is the total number of wins for player I across all their games. This value is taken directly from the data and never changes during the iterative process. Nji, this is the total number of games played between player I and player j. Nij equals wij plus wji. This also comes directly from the data and does not change. Okay, so in plain English, the formula says a player's new strength score is their total number of wins divided by a term that represents the combined difficulty of their matches based on the previous strength estimates. Okay, so now let's figure out our total games matrix. NAB just means the number of games that Alice beats Bob plus the number of games that Bob beats Alice. So as we can see, Alice beats Bob 6 times and Bob beats Alice 4 times for a total of 10 games played. And then just do that for every paired comparisons. Okay, so to start this thing off, let's just assume everyone is of equal strength and go from there. And here's our update algorithm expanded. Since we are assuming they are all of equal strength, we can just substitute that in for p of a of 0. For all of our step zeros, we're just going to assume an equal strength of 1. Okay, so after one iteration, our new strength estimates are Alice 1.333, Bob 0.63 repeating, Charlie 0.8, and Diana 2. Notice how the rankings are already starting to emerge. Diana, who has had a perfect record, has the highest score. Alice, who won a lot, is next. Bob, who lost the most, is the lowest. This single step has already given us a much better approximation than just guessing. Now we simply repeat the process to calculate p of 2. We use the p of 1 values we just found. We repeat this process over and over. With each iteration, the parameter values will change, but the changes will get smaller and smaller. We stop when the values barely change from one iteration to the next. Example, like when a change is less than 0.00001. At this point, the algorithm has converged, and we found the parameter values that maximize the likelihood. This is a task suited for a computer, but the math it's doing is exactly what we did in step 2, just repeated several times. The final approximations are the stable values that this process converges to. So one step I forgot to mention is that on each iteration, you should normalize your output. So this iterative update algorithm can produce parameter values that grow indefinitely, potentially leading to numerical instability. So it's just easiest to just normalize after each step. I mean, while the raw unnormalized parameters would technically yield the same log likelihood value in that specific iteration, the normalization step is an integral part of the algorithm's design to guarantee convergence to the maximum likelihood estimates. Without it, the parameter estimates would not be unique. Alright, so now let's take our new estimates that we just obtained from just doing 2 iterations and plug those into our log likelihood function and compare it to our initial guess that everyone was of equal strength. And to compare these two, we have to look at the relative likelihood. And we compute this by taking e to the power of the difference of those two numbers. In our case, we end up with roughly 43.5, meaning the updated strengths are about 43.5 times more likely than the equal strength guess, which is not bad for just 2 iterations. Let's program this and then get a result doing it many times. And so here we can see those values converged. And they converged after 564 iterations, which sounds like a lot, but the program ran in probably less than a second. And then if we do our comparison again, these strengths are 151 times more likely than our initial guess. Alright, and so if we wanted to use this to try to predict future events, we could set it up like this, put in our values that we found, and then as you can see, the probability of Alice beating Diana is very small, or conversely, the probability of Diana beating Alice is quite large. Keep in mind, in our data, Alice and Diana never played against each other, but due to the associations of the other games played, we have a pretty good idea of what would happen. So here's some pitfalls of the Bradley-Terry model. Before applying the Bradley-Terry model, it's a good idea to run a depth-first search on your data to make sure the graph is well connected. If the match data is too sparse or disconnected, the model estimates can break down or become unreliable. Another limitation is this model only accounts for win/loss outcomes. It assumes every match has a clear winner and loser. It does not handle draws. There are modified versions of the model that can incorporate draws, but that's a bit beyond the scope of this video. Maybe something to explore next time.